enough to say for the general population that male, female, and just to make the data work, if we do it by hand, simpler, I lumped, here are my findings for 1 year, which would have been in the early 2000s. This is everybody else. Latino? Other. So the question is, you see sort of how there's a gap there. Do I have enough information here to say for sure for the general population that whatever that general population is, that's what gets tricky because I don't really necessarily have a random sample of the population, but for the general sample of trick-or-treaters around this sort of area or region at these general times, that there's actually a difference between the general trick-or-treating rate of Latinos compared to everybody else. And the reason I lumped them together really was just to make the math easier to do on this. But there was sort of no particular African American or white difference in numbers. And so with this kind of question, two categories, and you want to see, is there a difference? In reality, this is called the chi-squared test of independence, is what we're about to do. Chi-squared test of independence across categories. Now, there's one, and if you do this, if you ever have a group of categories, this is called a conventional crosstab. If you ever have these, if you want to find out, is there dependence here or independence statistically, with 95% certainty, you need to perform a chi-square test. If you have any sort of like more robust program, like Stata or SAS or anything, it's done all the time, it's really easy, quick. It's a little tedious in Excel because it doesn't actually sort of do that for you. But the nice thing is sort of I get to show you that sort of how it's actually done. So you see how it's done. And normally this technique is only necessary if you actually have 3 or more of one of the categories. Why? Because what is this? This is 0.60% female for X for P1. Population 1, which is population Latino. 60% female. For population other, everybody else, this is minus 0.47. 47% female. Remember how you do that? You get that equal to Z, you divide that by P bar over 1 minus P bar over N1, which is 36, 43, 62, and then plus So what I'm going to do here now, and see you couldn't do this if you had a third category here. Then you couldn't do this. So with 2 categories, for 2 categories, a chi-square test of independence across these categories, which I'm about to do, is identical to doing the test we did in the first half of the semester. Is there enough of a gap between these 2 percentages to say for sure, does this rise to a Z large enough to say that there's a 95% certain difference between the actual populations? These are samples. These are the sample percentages. That's the old way of doing this with 2 categories. Essentially what I'm going to do here, we'll find the same p-value as this. And once you get to a third category, the reason I'm not doing 3 is that I don't want to waste a lot of time on the math. And the math gets longer. And that's why if you look at any sort of stat textbook, you can do a chi-squared with a 2 by 2, but you can also do a test of 2 percentages and see are you 95% certain they're different from each other or not, as long as you only have 2. Once you get to 3, you can't do that, and you have to do the chi-squared. Once one of the groups becomes 3 long, or this one becomes 3, either one becomes 3, then you can't do that. And so how do you do this then? You've got this, 30, 40 through 50, and you've got this, 39, 49, 55. You've got a total of 105 data points. What chi-squared then does is chi-squared is measuring the observed minus the expected squared divided by the expected. The observed minus the expected squared divided by the expected. That's what a chi-square test is evaluating. Expected is sort of the same and all. What the expected is